The biological treatment stage comprises a so-called activated sludge tank and a final clarification tank. The activated sludge tank is the place of nitrification and denitrification processes. In larger wastewater treatment plants, the additional step of phosphate elimination is carried out before these processes. Here in Halle, a so-called BPR tank is used for phosphate elimination. BPR stands for biological phosphorus removal, sometimes also called a BioP tank. Not all plants use a separate phosphate elimination stage, as this process can also take place naturally. The trend is for modern plants to increasingly use phosphate precipitation instead of elimination. But let's get back to phosphate elimination. Phosphate elimination takes place with the exclusion of free and dissolved oxygen. For this reason, BPR tanks are often covered. This environment creates optimum conditions for anaerobic bacteria to multiply and complete their task of eliminating phosphate. The other microorganisms in the wastewater are inactive during this stage, as, for them, there is either not enough oxygen or none at all. When the phosphate has been eliminated in the first stage, the water flows into the so-called denitrification tank. Here, it is no longer that the anaerobic, but the anoxic bacteria enjoy optimum life conditions. With free oxygen being excluded, anoxic bacteria thrive and multiply. They biologically convert nitrate and nitrite into nitrogen. What's the role of the mixers in the tank? They move the bacteria towards the food they are to convert, that is, towards the substances we would like to rid the wastewater of. The last stage is that of nitrification. Here, the wastewater is enriched with oxygen that is supplied by aeration units that are usually fitted to the floor. This creates a favorable environment for aerobic microorganisms that convert ammonia or urine into nitrate and nitrite, also referred to as nitrification. They also metabolize all carbon compounds and produce carbon dioxide. In these conditions, the aerobic microorganisms keep multiplying. Finally, the resulting mixture of activated sludge and wastewater is subjected to another denitrification process. Depending on the system design, recirculation pumps transport some of the bacteria back to the start of the process so they can perform further work. Some residual bacteria ends up in the sludge treatment process. The treated water flows back into the final clarification tank. Before talking about the final clarifier, I'd like to explain the reference values BOD and COD. At the beginning of this video, I told you where the wastewater comes from, namely from the municipal and industrial use, as well as from rainfall. Looking at the source is a decisive factor as it determines the pollution load contained in the wastewater. In other words, the wastewater composition determines the scope of biological treatment stages needed. Industrial wastewater, for example, must not be discharged directly into a municipal wastewater treatment system, as the pollution load contained is too high. A municipal wastewater treatment plant designed for wastewater from private households is simply unsuitable for treating industrial wastewater. For this reason, large chemical or industrial plants are often required to operate their own wastewater treatment plant. In such a plant, they usually only aerate the wastewater, as in many cases, they are required to remove carbon only. The wastewater is treated until it reaches the limit values for being discharged into a municipal treatment plant. This is where the reference values BOD and COD come into play. BOD stands for biological oxygen demand and COD for chemical oxygen demand. These values indicate the degree of contamination, how long the wastewater will need to remain in the biological treatment stage, and if it has been treated sufficiently. In principle, BOD and COD are two key values for selecting a treatment plant. The BOD refers to the amount of oxygen that would be consumed during 5 days of incubation at 20 degrees Celsius in order for the bacteria to oxidize all organic substances in a litre of water. We could also say, what do the bacteria need for their metabolic processes? The COD is used for direct chemical processes. It indicates the amount of oxygen needed to oxidize all organic substances contained in the water. An oxidizing agent decomposes the biodegradable and non-biodegradable substances and produces carbon dioxide. The COD is mainly used in the context of industrial wastewater treatment plants. Let's move on to the final or secondary clarifier, the last stage of biological treatment. The aim of this stage is to remove the microorganisms remaining in the water. Treated water flows continuously from the activated sludge tank into the final clarifier. Here, heavy sludge containing microorganisms sinks to the floor, and the lighter substances accumulate on the surface. A removal device moves the heavy substances to the middle so they can be evacuated. The lighter substances are skimmed off by a rake. The removed sludge is either returned to the activated sludge tank or pumped to sludge lagoons. The clarified water finally flows out of the tank via a drain channel. Everything taking place in biological treatment generally also occurs in nature. The only difference is that in wastewater treatment plants, the processes are carried out on an industrial basis.